In this presentation, we would like to introduce an energy-efficient dual-field elliptic curve cryptography processor for Internet of Things applications. Here is our outline. First, we will give a brief introduction on elliptic curve cryptography. Second, in proposed ECPN algorithm section and hardware design section, we show various design techniques across the algorithm, architecture, and arithmetic circuit levels to minimize power and energy consumption. Further, we will show our implementation results and compare it to others, including ASIC implementation results and FPGAs. Finally, we will conclude this work with the energy reduction of both fields when compared to the state-of-the-art designs. In 2005, elliptic curve cryptography, known as ECC, was standardized by NIST, and it offers a higher security level with a shorter key size than the other public key cryptography schemes, like RSA, which makes it perfect for IoT devices. However, those IoT devices could be extracted through side-channel attack during encryption or decryption. To prevent one of these attacks, double and add always algorithm is usually employed by inserting dummy operations. Thought double and add always algorithm can effectively eliminate the power variation and the corresponding information leakage. The additional dummy operations severely degrade both the computation performance and energy efficiency. Another popular SPA resilient scheme, the AND-array method, avoids using redundant operations while eliminating the power variation by storing the pre-computed points. However, the associated implementation complexity is significantly and causes additional power and energy consumption. In this work, we exploit various design approaches across the algorithm, architecture, and arithmetic circuit levels to maximize energy efficiency. The proposed elliptic curve point multiplication algorithm realizes SPA resistance with high area and energy efficiency by combining signed binary representation with the AND-array method. Moreover, the proposed hybrid modular arithmetic architecture, in which each arithmetic unit cooperatively performs modular operations, significantly enhances the hardware utilization and energy efficiency. Finally, the processor employs an energy-efficient data flow that effectively minimizes memory overhead during group operations. In this slide, we introduce our proposed elliptic curve point multiplication algorithm, which we will call it ECPN algorithm in this presentation from now on. The traditional AND-array method decomposes an ECPN computation into two operation phases, pre-computation phase and evaluation phase. During the pre-computation phase, multiples of the base point are first calculated and stored. For example, if window size W is 4, we need to compute from 2 dot the base point, 3 dot the base point, to 15 dot the base point. During evaluation, the complete ECPN is then performed based on the binary representation of the private key, from the most significant window to the least significant window, with W times elliptic curve point double operation, followed by one elliptic curve point addition operation in each window. Because of this operation regularity, the AND-array method is immune from SPA attack. In order to reduce the implementation cost and energy consumptions while achieving SPA resistance, we propose to introduce an additional key encoding phase to the AND-array method during ECPN computation, where the private key is encoded into signed binary representation with only 1 and -1 instead of 0 and 1 representation. Since every signed binary representation encoded window consists of only odd numbers, A proposed SBR and array needs to compute and store only odd points during pre-computation. So, half of the memory size is reduced, and we don't have to deal with the situation when any of the window value is 0. Here is the comparison table, which summarizes and compares the operation cycles and required storage size between DAA, the AND array method, and the proposed SBR and array algorithm. The proposed SBR and array realizes twice the reduction in both memory size and operation time at the pre-computation phase when compared to the traditional AND array method. To demonstrate the advantages of power and energy efficiency of the proposed approach, the figure below shows the simulated performance results of different ECPN algorithms for a 192 bits ECC implementation with a window size W being 4. The ECC design based on the proposed SBR and array algorithm demonstrates 10.9% and 30.2% lower power and energy consumption than other approaches. Further to the ECPN algorithm, different coordinate systems result in different performance even under the same ECPN algorithm. Traditional ECC hardware implementations for high-speed applications usually avoids the use of the affine coordinate due to the associated divider circuit cost. For energy-constrained IoT applications, however, the affine coordinate emerges as a better solution to energy-efficient ECC implementation. This figure shows the comparisons of ECC design based on different coordinate systems. The simulation results shows that, compared to other coordinate systems, the affine coordinate consumes substantially less energy, contributed by elliptic curve point addition and double operations. As a result, the ECC design based on the affine coordinate realized 42% lower energy per ECPN operation, despite having expensive division operations. This figure shows the proposed energy-efficient dual-field ECC architecture employing the proposed SBR and array algorithm and affine coordinate. It consists of a key encoder, a Galois field arithmetic unit (GFAU), and an ECC controller. The key encoder converts the private key to signed binary representation, and GFAU performs modular arithmetic operation in both prime and binary fields. The ECC controllers coordinates different modules, schedule data flow, and executes the entire ECC scheme. In addition to proposed ECPN algorithm and coordinate system, we propose the hybrid modular arithmetic architecture, in which each arithmetic unit cooperatively performs efficient arithmetic operation with a dedicated resource sharing scheme. Therefore, this optimization approach jointly optimizes arithmetic units together to maximize the overall hardware utilization and energy efficiency. This figure illustrates different arithmetic operations and corresponding data flow with the proposed hybrid modular arithmetic architectures. For modular addition, the input A and B are first stored in the register R and S, and then processed through the modular adder, which is similar for modular subtraction. For modular multiplication, the inputs A and B are stored in the registers S and V instead. The adder, originally used for modular addition, and the modular shifter together then complete the computation with multiple voltage steps. For modular division or inversion, the inputs A and B are stored in the registers S and V, where the registers U and R are initialized with the prime P and 0. The modular adder and subtractor for modular addition and subtraction are again reused to perform the extended binary GCD algorithm during the phase 1 modular division steps. The modular reduction operation during the phase 2 modular division can be effectively completed by reutilizing the modular shifter, originally dedicated only to modular multiplication with the registers S and V, initialized with 0. As a result, the modular reduction circuit, traditionally required for modular division, can be completely eliminated. Therefore, the proposed GFAU with the hybrid modular arithmetic architecture achieves an 29.7% reduction in energy consumption when compared to the conventional GFAU design. The proposed ECC controller is composed of Montgomery domain converting unit, an elliptical point addition and double processing unit. Among them, the domain converting unit first transforms the base point and then related curve parameters into Montgomery domain, and also inverts the final computation result back to the normal integer domain. Moreover, the proposed ECC controller architecture employs a data flow and a computation scheme that optimize both the memory access and storage for maximum utilization rate, as shown in the figure. The controller requires only 4 L-bit registers with almost full utilization rate. With the proposed data flow and computation scheme, the ECC controller achieves 11.9% lower energy consumption when compared to traditional methods. The figure above shows the ASIC layout with TSMC 19 nanometer technology. Our dual-fuel ECC processor can achieve 250 MHz, 14 mW with 83.4 kGs for the ECPN operation. A 192-bit dual-fuel ECC prototype with the proposed design approaches was synthesized using quarters and implemented and verified on Altera FPGA platform. The table below summarizes the FPGA implementation results of the ECC design, in which different optimization methods have been employed. The areas of ALETs and registers are both reduced accordingly with different optimization techniques. This table summarizes the ASIC implementation results and performance comparisons with the state-of-the-art designs. The proposed dual-fuel ECC processor realizes the more compact design with comparable speed performance, while consuming the lowest amount of energy and power. In terms of energy area product, which is a useful performance metric to evaluate the hardware efficiency for resource-constrained IoT applications, the proposed design substantially outperforms other ECC implementations by a factor of 2.39 and 2.69 over the prime and binary fields, respectively. An ECC hardware implementation for energy-constrained IoT applications must consume lower power and energy with high reliability. In this work, an energy-efficient ECC processor is presented to support dual-fuel computations with simple power analysis resistance. By applying all optimization techniques described above, we can reduce the energy consumption of the ECC processor by up to 31.5%. The ECC hardware implementation using the proposed design techniques achieves energy reduction of 51.6% and 50.5% for each GFP and GF2 to the N ECPN operation, respectively, when compared to the state-of-the-art ECC designs. And those are our references. Thank you for listening.